Thanks for the introduction. Thank you very much for the invitation as well to come and speak to you all today. There's a very exciting time to be looking at exascale systems, because while these things seem to have been a long way in the future for many years, they're now starting to happen. So this is a great time to look at things. My own background, so while I'm a computer scientist, I largely focus on areas like computer architecture. And in fact, I spent 15 years in industry actually designing real processors. So my background is both academic and commercial and industrial. So I used to design and build real supercomputers before I went back into academia. So I mentioned that it's a really interesting time to be looking at this. And here's a range of the exascale systems which we're aware of, really focusing on Asia and the USA. I haven't really listed any of the systems that might appear in China, which is the other place that exascale is going to happen very quickly, because it's less well known exactly what China is going to do. But one of the first things that really jumps out at you when you look at the exascale systems that will start arriving later this year and then will keep appearing over the next few years is they're very diverse. And we haven't seen this range of diversity for quite some time. And this diversity actually is a big deal. It has quite a big impact on all of us. So as a user of an exascale system, the fact that they're all going to be different is something we're actually going to need to take into account. And so, for example, I've included on here Fugaku, which is the current #1 supercomputer in the world. Technically, it's about half an exaflop, but actually its scale very much is sort of exascale in terms of how big it is, how much parallelism it uses. There's over 150,000 CPUs in Fugaku, and 7.6 million cores. So these are at a scale far beyond anything we've had to really exploit so far, and they pose a whole range of new challenges as a result. So I think Fugaku is sort of the first in the sort of exascale era, even though it's going to be one of these following machines, probably Frontier, which is going to be at Oak Ridge, which is likely to be the first official exaflop on the LIMPAC benchmark for the top 500. When that goes in sometime next year. You can see between these different machines, so the last four all going into the USA, Perlmutter is a mix of AMD CPUs, and we're all used to mostly using Intel CPUs, mixed with NVIDIA GPUs. So it's two different vendors. Frontier, which we think will be the first exascale machine, unless China springs a surprise, that will be AMD CPUs and AMD GPUs. Again, we're always used to using NVIDIA GPUs, but the first exascale machine won't be NVIDIA. It'll be a different kind of GPU. Aurora, which will appear a little bit later, it's been a bit delayed. That's Intel CPUs and also with Intel GPUs. There's new Intel GPUs coming out. So that's three different types of GPU in three of the exascale systems, NVIDIA, AMD, and Intel. And then El Capitan, which is likely to be a couple of exaflops actually, that's going to be all AMD GPUs as well. So in terms of your codes and the work that you're doing, ideally you'd like to be able to run on any one of those machines, wouldn't you? And not just have, say, a GPU code that runs on NVIDIA. You really want to be able to run on all of those. And if you're lucky, you run on all of them, not just any one of them, but all of them. And that has a whole bunch of implications for us in terms of what sorts of programming languages we're using, what sorts of libraries we might be using, what sorts of algorithms we might use as well. So it's worth keeping all this sort of thing in mind. Now, given that we think Frontier is going to be the first sort of official exascale machine, I've zoomed in a bit on the detail for this. And this is sort of the block diagram for one node of Frontier. And it's actually quite typical of all of the GPU exascale systems. And the important thing to notice about it is that it's flipping the model that we've all been used to. The network, this is a Cray system, so it's the new Cray Slingshot network. The network actually comes in and attaches to the GPUs. And then the CPU hangs off of the GPUs, rather than the other way around. We're used to the network coming into the CPUs are the master, they're the thing that's in control, and the GPUs hang off the CPU. The GPU is becoming the peer, right? So it's GPU first is sort of the methodology from now on for the exascale class GPU machines. There's only one CPU as well to all of these GPUs. This means that things like your MPI is going to have to run on the GPU. You're going to be sending messages from GPUs over the network directly to other GPUs, rather than having to go through the CPU. And like I say, all the other GPU exascale machines are of a similar architecture. For Frontier specifically, it's going to be something like 1.5 exaflops. All of the numbers are still a bit hush-hush because it's not officially released. Something like over 100 cabinets. Archer 2, which is going in at the moment, is 23 cabinets. So these are big machines, but actually they're just incredibly dense. The performance is, in terms of peak floating point, is going to be a lot higher than 4 times that of Archer 2, and that's because it's employing these next generation GPUs. About 30 megawatts. That is quite a lot of power. I think Archer 2 is going to be something like 2 to 3 megawatts, so 10 times more power. There's no getting away from that, and quite a lot of money, $600 million. So yeah, you need quite deep pockets for these first generation exascale machines. The exact hardware hasn't been confirmed either, but you can make some fairly educated guesses. The AMD Milan CPU is just coming out now. That's the follow-on to Rome, 64 cores in a single socket. There is a follow-on from Milan. It might be that one next year. We're not quite sure, but it'd be at least Milan. The GPU is probably going to be the MI200 AMD GPU, so not NVIDIA. Again, we don't know exactly what those are, but the current generation has just come out, the MI100, and you can look at the recent roadmap for the AMD GPUs, and you can kind of project forward and speculate a little bit about what the performance is likely to be. And it's going to be of the order, these numbers will be in the right ballpark, they won't be exactly right. So these are my guesses. About 15 teraflops double precision for a single GPU, about double that for single precision, and a really big number for 16-bit, and that will be using the sort of tensor core equivalent. So most GPUs have grown these tensor core small matrix vector units. NVIDIA did it first, but everyone's doing the same thing. And if you can target those, you get much higher performance. Initially, that was just for the half precision 16-bit floating point. Over time, the vendors are adding in support for the other precisions in those units. So it might be, we'll see higher peak performance for 32-bit and maybe even 64-bit if they get support for that in the little tensor units in the AMD MI200. And I don't know what the exact answer is. We'll have to wait a little bit longer for that to be confirmed. So that's my projection. But these exascale machines, they're a bit of a beast. And they are predominantly GPU based, and the GPUs are now finally sort of taking charge, and the CPU hangs off them, and this sort of a reverse offload model where there are certain things you really might not want to do on a GPU, and that will then go and run on a CPU somewhere. But most of the time, most of what you'll be doing will be on the GPU, and the GPUs will even be able to talk directly to the network and to each other directly over the network. So that's quite a big shift in what we've been used to with these GPU machines. However, I just want to emphasize, in case anyone takes away from that, that therefore the GPU is the answer. It isn't the only answer. And in fact, Fugaku, I'm very grateful that it's there because it kind of proves there are other ways of doing this. And what Fugaku has done, that the processor in Fugaku, which is the A64FX from Fujitsu, they basically took the most interesting, the most powerful technologies that GPUs use and bolted them into a CPU. So they use the high bandwidth memory, the HBM from a GPU, and then they've just got lots of cores with very wide vectors per core, and they produce a CPU that has the same sort of peak floating point performance, the same sort of memory bandwidth, and the same sort of energy efficiency as a GPU, but it's just a CPU. So it will therefore run whatever you wanted to run on a CPU. It will run flat MPI code, it will run Python, it will run your Julia or Rust or whatever language you come up with. If it runs on a CPU, it will run on this. So in some ways, this approach, this homogeneous CPU, but with the GPU technologies cherry-picked, is almost the sort of perfect combination. It's got the performance and energy efficiency of GPUs, but they're much easier to use, the ease of use of a CPU. It does mean you end up with very high levels of parallelism. So if Fugaku is currently about half an exaflop and is already 7.6 million cores, then you're looking at 10 million cores plus. The next generation might be slightly faster, but that you might be a 10 to 20 million way parallel to make the most of a system like that. But it is possible. So I think the important thing to take away from that is we shouldn't just be wholesale rushing to port every code to GPUs, thinking that's the only way forward. It really isn't. There are other ways of doing it. And multiple vendors are, while A64FX has been the first to do this in this generation, there are other vendors doing similar things. Even Intel, Intel has a CPU planned with high bandwidth memory, wide vectors, and so on. So it's worth keeping that in mind. This GPU thing isn't the only way forwards. That means the implications of all of this for us is that we've got quite a lot of work to do. So figuring out what hardware we're actually going to target, and it's not just about CPUs and GPUs, but there are other kinds of accelerators as well, and even accelerators within our accelerators, right? So the GPUs now have these tensor units for doing these matrix operations. That's an accelerator within an accelerator. That's not something that will be easy for a compiler to target. So you might have to handwrite some code or use a library to be able to really exploit the full performance of these next generation bits of hardware. So there's lots to think about just in terms of what hardware to target, but also what software we need to target. And that becomes even more crucial now we have this increased diversity, and also that in some systems there's heterogeneity, CPUs and GPUs, and other systems there isn't, more homogeneous, like Fugaku. So the choice of programming language becomes even more important. In the past, you may have got away with using a language that was vendor specific because maybe that vendor was the only one supplying the hardware. In the future, you absolutely can't do that. It would be suicide to tie yourself in, paint yourself into a corner using a language that's vendor specific. So this will mean trying to use things like OpenMP, which does now support GPUs, or languages like SYCL, which is at the heart of Intel's new DPC++. So SYCL is a parallel, SYCL 2020 is the one to go for actually. It's a parallel programming standard, an open standard for parallelism in C++, or using things like domain-specific languages where you insulate yourself and your programs and your algorithms from the specifics of the hardware, and inside the domain-specific language, you would then generate code specifically for whatever platforms you were targeting. So that at that point within a DSL, it's not such a big deal to use a vendor-specific language because the end user and the end user code isn't then kind of exposed to that. Good news is, while this is all very complex and there's a lot to think about, there are some initiatives underway in the UK to help find a way through all of these issues. Obviously, ExCALIBUR is the one that you may be the most familiar with. That's the one that we're kind of talking about a bit today, but also others like Asimov, and actually Lee from Rolls-Royce will talk about Asimov a lot more later on, so I'll leave that to Lee to mention. The other good thing, we're actually in a very strong position in the UK in terms of having access to all of these very diverse architectures. I'm very involved in Tier 2, so I'm the PI for the Isambard Tier 2 system. And within that, we've deliberately put together a very diverse range of hardware so that people who are developing software can try all of these different architectures and start to learn what their advantages and disadvantages are. So that includes, recently we've added some of these A64FX CPUs that are in Fugaku. So you can actually try some of that in the UK as of now. We've also in the same system got some AMD CPUs, we've got the latest Intel CPUs, we've got the latest NVIDIA GPUs. We're shortly going to add some AMD GPUs as well, all in one system. So you can actually try these different things out and do nice rigorous comparisons between the different architectures. But that's just Isambard, and there are actually lots of other really good Tier 2 systems in the UK that you can try, and therefore prepare yourself for some of these exascale solutions that are coming down the chute. I've included two links. One's to a site that Edinburgh runs, and then the second is to the EPSRC site for where you can find the list of all of the different Tier 2 centres. If you just Google search EPSRC and Tier 2, I think it finds that link for you. And then of course, we've also got Archer 2 now coming online. We've got the first 4 cabinets of Archer 2 in use today. That's something like 120,000 cores, something like that, 130,000 cores. but the rest of the cabinets actually arrived within the last week, and they're starting to get brought up and updated and integrated now. So later this year, there'll be something like 750,000 fast AMD cores for you to use. It's all CPUs, there's no GPUs in this, but that will be available a bit later this year, which would be good for starting to try scaling up to sort of order of million-way parallelism. So we really are in quite a strong position in the UK. The tier 1 and tier 2 organization is really good. I've just been talking about Archer, but of course there's also the Met Office systems for the part of the community in that space, and then Dirac for all of that, that side of things as well. Within the tier 2, there's really a very broad range. It was recently refreshed with some new systems and some new technology. I've mentioned Isambard and our A64FX system. We've actually got 72 nodes of A64FX, nicely with the Cray software stack, which many of you may be familiar with if you've used our national systems like Archer, and lots of different compilers to try. And we're up to about 500 users on Isambard already, and we're very inclusive. So if anyone would like to have an account on Isambard, in fact, next month, late next month, we're going to run our first hackathon on these new processors. So if you'd like to sign up for that, just apply for an account on Isambard and drop me an email, and we'll happily invite people along to our first hackathon for A64FX. And the other tier 2s have a really wide range of different exascale class hardware. So Cambridge's CSD3 system has got lots and lots of NVIDIA GPUs. They're getting some of the new Ampere ones that have 80 gigabytes of memory per GPU. So those are really tremendous. They've got lots of memory and lots of bandwidth to that memory. Edinburgh's also got a system with lots of NVIDIA GPUs. Jade 2 has one of those dense GPU systems. That's quite a different packaging where you can combine those for doing, it's particularly well optimized for machine learning type applications, actually, the DGX2 type system. There's a new system in Northern Ireland, which is using AMD CPUs and GPUs. So this might be a good way of trying out some AMD GPUs. There's a materials and molecular modeling hub, which is mostly x86 for people doing those sorts of problems. Similar sort of for Midlands Plus. And then we've even got a system which use IBM Power CPUs and NVIDIA GPUs. This is like a little bit of the Summit and Sierra big systems in the US that are sort of in the top 10 of the top 500 in the world at the moment. So there's really is a little bit of everything in the UK. That's quite an unusual situation. It's very deliberate, and it means that you can take your codes and your algorithms as you're developing them now, and you can really start to get them exascale ready. So we're in a very strong position, and you can apply for accounts on all of these systems. In fact, very timely that there's a new core that EPSC has just released in the last week or so to get access to these systems, and in fact apply for a reasonable amount of time on them. Typically for the tier 2s, requests are in a sort of a few million core hours. On the tier 1, so for Archer 2, you can ask for a lot more than that. And the cores just come out. You've got until the end of April to submit, and the form you have to fill in, the proposals, not too onerous. So you can actually go and apply for time on all of these different systems. And we're always very happy to have people applying for time on Isambard if you want to try out these different sorts of architectures. So do consider that. I mentioned ExCALIBUR, and I'm actually on the steering committee for ExCALIBUR. So I wanted to include one slide just to remind everyone what ExCALIBUR is all about. And it's a 5-year program really to get UK's science space ready for exascale. And it's focused almost entirely on software and algorithms. So it's not really about hardware. And it has a couple of different programs within that 5-year project. First one being knowledge integration. The second one, which has been ramping up a lot recently, has been high priority use cases. And those spread across the spectrum of Met Office, UKRI, and UKAA, so the sort of fusion energy side as well. Emerging requirements for high performance algorithms, the cross-cutting research. There's a call for the cross-cutting research on the sort of UKRI side. That's coming out within the next week or so, so keep your eyes open for that. And then also a little project for proof of concept hardware, and that's something we've kept about 10% of the budget to actually look at pre-commercial hardware. So as new things are starting to appear in the lab, trying to build up some experience with that so that we're not taken by surprise towards the end of the project and something exciting and new comes out that we haven't taken into account, and then that leaves us at a disadvantage. So that's ExCALIBUR, and I think some of the other talks later on will go into that in a lot more detail. So that's a bit of a whistle-stop tour. Hopefully it's given you some idea of what's coming in terms of exascale architectures and what the UK is doing to get us ready for that. The takeaways that I'd like to summarize really are, we have now got quite a lot of exascale related activity going in the UK, predominantly with ExCALIBUR, but there are other activities too, like Asimov, which Lee will talk about for Rolls-Royce in a minute. And also all of our tier 1 and tier 2 systems. Actually, we are in a pretty strong position. So it's up to us to take advantage of that. We're going to have to get our codes and our users ready for this diverse future. And in the past, we really had a very homogeneous, it really was all Intel CPUs. And if you use GPUs, they're NVIDIA. It's very sort of homogeneous. You can see for these next generation systems that it's all very diverse. Three or four different vendors of CPUs, 3 different vendors of GPUs, and almost every combination is being used in an exascale system somewhere. So we need to take that into account. However, whatever solution you end up on, the thing they all have in common is they're all very, very, very parallel, massive parallelism. At least tens of thousands of nodes, up to millions of cores. So these really are kind of orders of magnitude more parallelism than we've had to worry about in the past, even with Archer 2, with sort of order 1 million way parallelism, talking 1 or 2 orders more parallel, even beyond that. So this is something we really need to be planning for, getting ready for, and starting to use what we've got today, tier 1 to tier 2 and ExCALIBUR, to get ourselves ready for our exascale future. And with that, I'll just leave a couple of links up. I think the slides will be available afterwards so that you'll actually be able to click on the PDF of these later on. The link for my research group and what we do is at the top. There's a new page for ExCALIBUR describing what the ExCALIBUR project is about. So you can find out a bit more detail there. I've included the link for the tier 2 so you can see all of those, and feel free to get in touch with me afterwards if you want to talk any more. And that's me done. Thank you.
Thank you very much, Simon. So that was a very nice overview, I think, of the landscape as it stands and really sets up the rest of the meeting. It was a really great talk. So I can see a couple of questions are coming through on the Q&A thing, but just to highlight, in case anybody missed it in the chat, if you want to speak to the panelists, please do type into the Q&A facility and the questions can be read out. If you don't mind, I just have one quick question. Cool. Myself. So in some ways I say it's a quick question, it's kind of the question. So given a lot of the audience here will be domain scientists focused on smooth particle hydrodynamics as a method, given its similarity to the likes of molecular dynamics, for example, do you feel as though the community should be focusing on relatively low level approaches? So there's a bit of a drive in the community toward GPU acceleration, the use of CUDA, so on and so forth. So perhaps that level, OpenScale, OpenMP, that kind of level, or maybe at a higher abstraction, SYCL, or perhaps even higher, sort of a domain-specific language approach. I mean, what's your personal feeling given your knowledge of the exascale landscape that's coming up?
Yeah, sure. So there's no one silver bullet for this, and that's what makes it so hard for everyone. There are some things definitely to avoid though, and there are some things which are more promising avenues to explore. So the things to avoid are anything that's vendor specific or vendor proprietary, and that's from whichever vendor, it doesn't really matter because of this diversity. So if you write, I'll be very specific because I think these are such important points. If you write CUDA code, it won't run on most exascale supercomputers, right? If you write anything that relies on, I won't just single out NVIDIA because I want to make the point. And Intel's DPC++ is an open standard. It's SYCL 2020 with some extra bells and whistles. If you write code that relies on those extra bells and whistles, that won't run on any of the other exascale systems either, right? So that's that's the point, is you need to find a way of writing your code and capturing your algorithms that will run on any one of those, because which one will we end up with in the UK? We have no idea today, and we won't know for some time. And you need to make progress in the meantime. So that means that the more promising choices are for C++, the sort of standard SYCL 2020, which by the way does have pretty much everything you need in it now. It's literally just come out in the last, it's been ratified in the last month or so. So this is a hot off the press thing. But it's strongly supported by Intel, and it works well on all the platforms. So it'll work on NVIDIA, it'll work on AMD, it'll work on Intel, it'll even work on ARM, right? So for C++, that looks like a good choice. At lower levels, if you want the pragma style of programming, you would definitely want to go for OpenMP instead of anything that's vendor specific. So use OpenMP, not OpenACC. If you've got OpenACC, the good news is porting that to OpenMP is really simple. It's very straightforward. Even more low level, OpenCL and CUDA. Again, CUDA would be a big mistake, but if you've got some, it's easy to convert it to OpenCL, or this other thing called HIP, which AMD have come up with, which basically lets you fairly trivially port your CUDA to run on AMD GPUs. I don't think that works for Intel yet. So at that lowest level of CUDA, OpenCL, HIP, there isn't really a good answer. Well, there is a good answer. The good answer would have been OpenCL, but none of the vendors like you using it because it makes it too easy to pull your code between the different vendors. It's not a technical reason, it's a purely marketing reason, right? So actually OpenCL even today runs just as well as CUDA does on NVIDIA GPUs, but you would not expect that, would you, from any of the marketing that goes on? So that lowest level is probably not one you'd want to use for handwriting code, but any of them would be a reasonable target for generating code. So if you have something like a domain-specific language where your software generates the code that actually runs on the hardware, then actually that's not too bad then if it uses CUDA or OpenCL or HIP or OpenACC or OpenMP, because your end users and your end user program isn't directly then written in that code. You just need to port the generator to do that. So that's the main thing. I think MPI is likely to be the solution for the internode, but within nodes, because there's no one silver bullet, just try and not paint yourself into the corner by relying on something that's vendor proprietary, whoever the vendor is.
Thank you. So 2 questions have come through. I'm slightly conscious of the time. So I'll ask them in reverse order because I think one ties back to what you just. Xiaohu Guao from STSC has asked, do you have any sort of insight into the performance difference of HIP on AMD versus CUDA on NVIDIA?
In my group, we do quite a lot of benchmarking across different processors. And from what we can see, when you convert CUDA to HIP and then run it on an NVIDIA GPU, it just runs at the same speed as it did before. So there's not really any overhead of doing that on the NVIDIA GPU. And then when you run the same code on AMD, it runs about as fast as you would expect for what we've tried so far. So then you're looking at, if you just look at the peak hardware performance of the 2 GPUs, if you compare memory bandwidth and peak flops, that normally gives you roughly the right ratio for how well they're going to perform. AMD's lagged a bit behind on performance until this latest generation, but the MI100s and MI200s, they're right back up being very competitive with NVIDIA on performance, but actually much more competitive on price, which is why we're seeing so many AMD GPU machines at Exascale. They've really been out competing NVIDIA on price performance.
Thank you. Okay, so I'll just very quickly cover the last question. So it's from Michael Bain from the University of Liverpool. What do we think the role of emerging tech such as FPGA is in Exascale? We talked obviously a lot about GPUs. You might lump FPGA with GPU perhaps, or what's your thoughts?
So I think FPGAs have been this interesting possibility for a long time, and we've never really cracked them in a general purpose sense for high performance computing. There have been a couple of specific things where they've been evaluated in detail, but the number of successes we've had where they've outcompeted GPUs, or in some cases even CPUs, has been relatively small. I think some things have been changing. They're getting easier to program with things like OpenCL or SYCL, and there are more projects evaluating them seriously to see if they are becoming easier to use. And in fact, even within ExCALIBUR, there's a big hardware enabling software project to build a test bed of different FPGAs and see what you can really do with that. So, so I think the answer right now is we don't know, but we're trying to find out. And they are promising in certain areas, but actually it's quite tricky to beat. If you've got memory bandwidth bound or float bound codes, it's quite tricky to beat GPUs and CPUs.